Okay, so moving on to your next chapter, community ecology. Now we're finally getting what I actually did one of my degrees in. So my master's degree, I was actually working on the community ecology of seagrass beds. You wouldn't think much of a seagrass bed because it's just a plant, right? And it's actually a flowering plant. I think I showed you some of the flowers before. But it turns out that seagrass are keystone species. They help to structure community, bind sediments, clear water. Things live their entire life in the seagrass beds. Things come in and migrate through. So maybe hunting grounds and nursery grounds, that kind of idea. Critical environment. We don't think about it. We go in, we walk through it, drop a boat anchor, rip it up, that kind of idea. But we were studying that, these assemblages. Actually, the site I worked at in St. Petersburg is intriguing. Very sad, but a boy apparently drowned back in the 1980s. So the state went out, and the area on the bay where the boy had drowned, they dredged it, and flattened it out, and make it safer, which makes perfect sense. But they ripped up all the seagrass. So there was a project to reestablish the seagrass in the bay, and it gave us this chance of studying the replanted seagrass versus right next door to it, the natural bed that had never been disturbed, and to see how community structures work. So it was intriguing research. It was a long-term study. It was like a 13-year study that I got to be involved in. So it was intriguing, but it was still community ecology. And when you did samples, you had to look at everything that was in the cores, every worm and fish and clam and of course seagrass. It was very taxing work. So intriguing, but taxing. So that's what this is. It's the assemblage, everything that's there. Even this little guy. Why is this guy carrying an urchin? Or you might see a crab that's got like anemones on its chile, the pincers. You could shove an anemone in someone's face, that kind of idea. How do they get these associations? Or you might think of an anemone fish living in an anemone, that kind of idea. How do these assemblages arise? What are the associations between organisms? So I've been using this word for chapters. I noted to you, start of the semester, and certainly in Bio 1, if you had me there, that unfortunately in science, like biology, when you're talking about one thing, you're talking about something else. So I had no choice but to use this word before, and I know I defined it many times for you, but the niche is the fundamental role of the organism. It's what you do. By definition, no two species can occupy the same niche at the same time. And that's what this is getting into. You're going to compete. Now, by definition, one dies, but again, that's by definition. It doesn't have to happen. You might get one that leaves, or stratification, they go a slightly different area, and therefore don't have to directly compete, that kind of idea. But it is your role. Now, even going back to the major terrestrial dinosauria, for example, except birds, they died out, niches opened up, which is one of the reasons why we talked about it even way back then in the first unit. And that allowed things like mammals to access these niches that were unavailable at that time when the major dinosauria were there. And, flash forward 65.5 million years, and here we are having a bio lecture. So this idea of a niche is very important. Now, there are two kinds of niches, the fundamental niche and the realized niche. See if they have the picture of it. They don't. So I can bring you one. Think of like barnacles on the side of a rock. So the fundamental niche would be, if I get a bigger picture of it, it's too close up. Okay, so stick in fundamental niche. Fundamental just means that, hey, if I could take all of this, I'm going to take all of this, but I'm going to compete most likely. So instead of getting the fundamental niche, I get the realized niche. So that's the kind of image I'm looking for. Okay, gotta put the whole thing in. NICHE, there we go. Okay, so there you go. Like this. If I can take everything for myself, I'm going to take everything for myself. That is my fundamental niche. But because I'm competing with someone else, I don't get that. I get this little piece. That's my realized niche. Again, it's not any more complex than just that. So with this interaction, we have this plus minus system. Obviously, plus means beneficial, negative means somebody somehow gets hurt, and of course, zero has no effect. These are the interspecifics, like between species interactions. These are the common ones, and these are the symbioses. People, again, I mentioned this before, love to make mutualism symbiotic, like synonym with symbiosis. I should say it that way. But mutualism is a kind of symbiosis. Parasitism is a symbiosis, commensalism is a symbiosis, facilitation is, herbivory, carnivory. There's a lot of symbioses out there. But again, they tend to make synonymous symbiosis with mutualism. Mutualism just means that everybody benefits. Parasitism, one benefits, one gets hurt. Commensalism, one benefits, one gets nothing out of it. Facilitation, just by being around, you benefit others, that kind of ideas. There's a lot of interactions here. So there's parasites, They could be inside of you, they could be outside of you. So maybe a tapeworm inside of you, maybe fleas outside of you, that kind of idea. Obviously, the parasite is benefiting and you are not. So it's still a kind of symbiosis, though. It's just somebody doesn't have a good relationship. Obviously, direct competition, you might get everybody getting hurt, that kind of idea. Predation, obviously the predator benefits, the thing getting eaten does not benefit, that sort of idea. Same with herbivory, the herbivore benefits, the thing getting eaten does not benefit. Again, it's no more difficult than that. Mutualism, everybody benefits. Commensalism, one benefits, one doesn't. Show you the picture on that since they're there. This is a great example of commensalism, a water buffalo. So in this case, the buffalo just does what it does. They're not like clean eaters. They have a patch of dirt, grass, and they rip it up and insects go flying. So the buffalo are after grass. The birds, though, they pick off the insects that go flying when the buffalo rips up the grass. So the birds are benefiting by the buffalo doing what it does, but the buffalo gets nothing out of the birds being there. So it's commensal. One benefits, one gets nothing out of it. What was I? And then facilitation. Again, just by being there, you do what you do, and others might benefit. They give you an example of it as well. Juncus. There you go. Juncus. It's a saltwater marsh. Notice when Juncus is there, more plants tend to do well than when Juncus is not there. Juncus isn't out there to help anybody. It's just doing what it does. But by doing what it does, it has a chance of benefiting others. That's facilitation. Now, I've also mentioned this before, mimicry. It came up in another lecture. Again, talking about one thing, you're talking about something else. So you get some that are just directly dangerous, and they have maybe a coloration issue that says they're dangerous. You might get another that's equally dangerous and has a similar coloration issue. Or you might get one that's dangerous with a coloration, another one that's not dangerous, but has a similar coloration. And that's what this warning is. Red is often a color in nature saying, stay away, I might get you, and that sort of idea. So notice two kinds, Batesian. So a harmless species mimics a harmful one, and Mullerian, they're both harmful. So here, this is just the camouflage. I remember the first time I saw this, you can see the granitic rock. It's granite, a kind of granitic rock. I didn't even see the frog the first time I glanced at it. It blends in so well. Frogs can be ambush predators, so kind of keep that in mind. There's a poison dart frog. Again, red is not unusual. I've shown you before, they don't have to be red. There's blues and yellows and greens, but red is not unusual. So that's a posomatic saying, don't touch me, I'm dangerous. And then Batesian. So this is just a larvae. It's not dangerous. So a harmless one mimicking something that is dangerous. And then Mullerian, everybody's dangerous. And they look like each other, that kind of idea. So a lot of ways you have interactions out there, and species learn, just better to stay away, that kind of idea. So mutualism, everybody benefits. This is an acacia tree. In this case, thorns do a pretty good job, but the ants are also really good at clearing things away. You can get swarmed by the ants. So the ants are benefiting the tree. The tree also swells with like sugars and proteins that the ants can collect and feed themselves with. So everybody benefits, which is why it's mutualism. There's your commensalism again, and of course, facilitation. So ecology really looks into, again, how all these species are interacting and how they're interacting with each other. So species richness is just the total number of species out there. And then you can look at abundance. But two things here. First off, with species richness, there's a new idea out there. I mean, by now it's been around for a while, that can use species richness, but that's really focused. So maybe go towards taxonomic richness. For example, I might say, wow, I did a survey at the Del Mabry campus, and there are 4,000 different species here. Sounds pretty cool, huh? Only to find out they're all cockroaches. And there are actually 4,000 different species of cockroach. So does that really tell you much? No. But if I said, yeah, there's 4,000 different taxa here. Wow, that's a whole bunch of different things that are at the Del Mabry campus. So a very different idea in that regard. And then abundance. The note there is some things are naturally rare, and we need to be aware of that. So you can't say, well, I love this, therefore I'm going to go and artificially bulk it up in the environment. That could actually be detrimental to the environment. So we got to be careful. We got to go back and do surveys. What historically has been here? How many's been here? What are they doing now and why? And then do we need to do anything about that? And it could be anything. Maybe we built a road and now we got to deal with that. It's affecting migration. It's affecting mating. We got to deal with that. Again, understanding that some things are naturally rare. So here they're just looking at composition. Again, both of these might be natural compositions. You can't look at this and say, wow, look, A is dominating. That's bad. Let's cut down A. Maybe that's how it's classically been and it's how it's supposed to be. You need to look at historical evidence. And then this one's saying, well, it's nicely distributed. So You might think, well, this is how it's supposed to be. Well, maybe, maybe not. You have to go back and see what has it been historically, what is it now, and why, and then make your appropriate decisions. So trophic means food, feeding. There you go, feeding. So that gets into these things called food chains and food webs. The food chain is much more direct, the A to B to C to D. Food webs are much more complex, and it shows not just feeding, but we're really showing energy flow through the system. So notice here, the A to B to C to D, it's direct. This is the food chain. Most people focus on food chains because, again, they are more direct, a little bit easier to study. They may not be good representations, however, of the bigger picture, but they give you an idea. So the primary producers are where we typically start. They're the ones harnessing solar radiation. Obviously, phytoplankton, plant-like organisms, like in an aquatic setting. Obviously, and of course, your plants. They set like energy budget to the system. So this harnesses the energy, and then the primary consumer, obviously at the plant, and then the secondary consumer eats the thing that at the plant, and then the tertiary eats the thing that ate the thing that ate the plant, all the way up to the apex predator. Now, here it stopped at a hawk. Could there be anything that eats a hawk? Yeah, maybe a human does, that kind of idea. Not that I'm advocating such a thing. Same in the marine setting. There's no marine here, but an aquatic setting. So plant-like to the animal-like that eats the plant-like, to the fish that eat the zooplankton, the bigger fish eat the smaller fish, all the way up to the apex predator. And I can't think of anything that naturally goes after an orca, except maybe a human. And even then, that takes massive technology. And if I was going to put just an orca versus a human, my money's on the orca. So again, it's an impressive dolphin. So it's just showing you the flow of food, yes, but in essence, the flow of energy. Now, this is a very simple food web, but it gives you an idea of all the different ways in which energies can flow. Although it did give me a little bit of a chuckle seeing humans here. Are we part of a marine setting? Yeah, sure. I mean, we go out and fish. Can anything at a human? Sure. So all these arrows are pointing to humans. I mean, like all this energy is going to us. But, it does happen sometimes that, something might eat a human. But again, generally speaking, no. So yeah, fine. We can go after and get all these things. We may not be going after the phytoplankton directly. We might go after krill. Who knows? I worked with it directly in aquariums. We would, not me specifically, but people would catch it and they would sell it to places like SeaWorld or Florida Aquarium, whatever. And then we would use it to feed our animals. So sure. And then on your way up the food chain. So it's intriguing, but it's just showing all the different ways in which food flows, but certainly how energy flows up to, again, including things like the apex predator. So these are hard. These are really hard to figure out. This, again, is a very simple food web. I had a buddy, I was my master's, he was doing his doctorate at the time. He spent 10 years figuring out mango food webs. It was so hard to do. Very impressive research, in my opinion. So people often focus on like a smaller view of these things, showing the flow of A to B to C to D, that kind of idea. So once we're looking at that environment, we could talk about, is there any species that dominates? Now, this could be the most abundant just by numbers. They have sheer, just like huge impact. Or it could be just by what they do. So I was noting seagrass. Seagrass are a keystone species. So not only are they keystone, they're also ecosystem engineers. These are like within the keystone species. These structure community. Just by doing what they do, they structure. You don't have to have a lot of them. Here they noted a beaver, a single beaver. How much like influence can this beaver have on the entire environment? Huge. It fells those trees, makes the dam, radically alters the environment. And it's just a beaver. So unlike the dominant species where it's like by sheer numbers, keystones, just by doing what they do, have huge impact. Termites, same kind of idea, not just the huge mounds they might make, say like in Africa, but the subterranean like tunnels they build as well can have huge impact. Earthworms can have huge impact, this kind of idea. So we go out and we study, what things are doing, including humans. Humans, do we qualify as dominant, keystone, or both? I think I read an article saying we actually just hit 8 billion humans on the planet. We do have population clocks. Now, these are obviously statistics. No one's going out and counting heads. I don't remember where I saw that article, but clock. Wow, did we really hit 8 billion? We did. So again, this is just by numbers. Is that a lot? It's hard to say. That's one of the issues in ecology that's kind of challenging, and my computer is deciding to be fussy again. Let's close that. Maybe that's what's giving me a problem. So it's difficult to know, how many humans are too many humans, and that's also ethical issues as well. So I'm not trying to get into that discussion. But are we affecting by numbers? Are we affecting by keystone? Again, both. These are challenging things to deal with. So seagrass can be it, this beaver can be it, a lot of things can be it. And then we look at the disturbance, with a lot of humans, we obviously have huge impact on the planet. So is that okay? Is it not okay? Again, um, we view things as data comes in. So now we kind of look at it. Is a lot of disturbance okay? Is intermediate disturbance okay? Is no disturbance what you want? I like the fact that they bring up fire. Fire is obviously a huge disturbance. I know I talked about it before. I think I mentioned the eco area at USF. So you have USF Tampa, Fowler Avenue, Fletcher Avenue. On the Fletcher side, there's this big area I showed you that USF owns. At least they used to. I think they still do. It's called the eco area, and they have it gridded out, and they go and burn like one plot every year, one plot every 3 years, one plot every 5 years, one plot every 7 years, and then look to see how disturbance works. Fire is a huge one, whether it's from a lightning strike or human activity, whatever it is. And how do species respond to this disturbance? And we found that intermediate is good. And I was noting too when I brought up fire ecology, I mean, put good in quotes. The intermediate might be better than others and that kind of idea, but this all depends on the environment. You really got to study a lot to understand what this environment uses. So again, it's complex science to say the least. But with the fire one, they were noting, how species kind of adapt to it. And we noted that when we had fire suppression, that invariably you're going to get a fire that outbreaks, a lightning strike. And there you go, you got a forest fire. And if we had fire suppression and never had smaller fires, now you get this massive forest fire that outbreaks. So we're finding that low disturbance may not be so great. And then high disturbance may not be so great. So it's tough. And I think I showed you this in lecture, the Yellowstone fire back in the 1980s, and how that was an example of how we were learning as we went and how we have to know that environment and what works for that environment like this. So it's devastating to our eye, and it can come back, but this is talking about primary versus secondary succession. That being said, and let nature do what it does. Don't ever set a fire, tend to your campsites, be responsible, the whole works. Let nature do this. Let the professionals do this. Let fire ecologists do that. Scientists do it, that kind of idea, the forest rangers. Let the people who are professionals deal with this. If you're going out and camping, be responsible what you're doing. But we study this, how things deal with disturbance. And that gets into these two phrases I just used, primary versus secondary succession. Primary means there was nothing there to begin with. Now something kind of comes back. And so that might be like a volcano. So you have bare, virgin, igneous rock. There was nothing there before. Now you have igneous rock. And then things are beginning to come in. And they're beginning to take the rock and break it down to soils and sediments. And then you get the plants that begin to come in. So you have the annuals that come in, and the perennials that come in, and then the shade intolerance come in, the shade tolerance come in. And then once you get to the shade tolerance that come in, now you have an upper story, so a canopy, and an understory, the ones that like shade, and you build up towards a climax community. That's primary. Secondary would be there was something, it got knocked back, and now it's kind of starting up again. Maybe like this. There was a forest, a fire happened, it got knocked back, and it's kind of starting up again. So that might be a good example of a secondary succession. So this too would be secondary as well. And they were noting glaciers. They have data all the way back to 1760 saying there was a glacier here and it's been retreating for obviously centuries. Not many things live in ice. So as the ice retreated, things began to come back all the way up to your climax community. So human disturbance obviously happens. I talked about this coral reef disturbance before. I mentioned that even all the way back like in the 1950s and 60s, and Jacques Cousteau was out there showing, hey, look at what's happening to these reefs. Humans are having impacts. We need to be aware of this and hopefully do something about it because we're transforming from vibrant communities to actual just wastelands of areas to it. Trawl nets are well known to do this. These big like football field size, like soccer field size pitches that they drop these huge net with these drums and they just collect everything and they leave like vast wastelands of no recallination happening after a single pull. It's just quite devastating. Some of these fishing practices, I've actually heard people liken trawl nets to clear cutting in a rainforest. It's that devastating. So it's something we need to be cognizant on. Can we get what we need in a sustainable manner? And we're still working on that kind of issue. So obviously then where you are affects. I mentioned the tropics before in the first chapter we did, chapter 52 for this last block. I was noting how particularly in tropics, when we have disturbance, it can be really damaging because the soils are so depleted in nutrients. There's so much moisture and humidity that you get this like huge like leachate area, and all the soils just lose their nutrients. So it's hard to come back from disturbance. So it's not to take away from temperate zones, like a temperate rainforest. The disturbance is still disturbance, but we need to be aware of, where are we? What kind of disturbance is happening, and how can we work with that kind of disturbance? So, and that means understanding the environment. How does species richness vary from a tropical zone all the way up to, all the way up to the tundra, whether you're going all the way up to the Arctic or to the Antarctic? How do these change? You're down in the Antarctic and you're dealing with penguins. How is that different than being way up in the Arctic and dealing with, I don't know, a polar bear? How do you deal with these things? So it's challenging, and that's why we hopefully look towards professionals who know the area well, and we can listen to their expertise. So there is that gradient that changes. And remember, we can chronicle that change. It is solar energy and how it distributes, but also water availability. That should sound familiar. The climographs that we talked about back in chapter 52 for terrestrial areas, those are the two main things, temperature and water, that really do affect the area. A little more challenging dealing with aquatic settings. You have to deal with salinity, you have to deal with the photic zone, you have to deal with again, like temperature issues. So you have a number of things to deal with, salinity, temperature, and of course the photic zone. So it's a lot of complexities of these things. But in the terrestrial environment, of course, evapotranspiration is important. Plants obviously play a role. How much water is in the atmosphere plays a role, and we can chronicle that. Same with disease. People forget about this all the time. Disease has a huge impact on evolutionary issues. So we track that. How does a virus affect not just an individual, but a group? Can it lead to extinctions? We've shown you, like in frogs, how it can. And therefore, we looked how things transfer. We've talked about vectors. I was noting how poor snails get just hammered left and right. We're talking about mollusks, how a lot of things eat snails, but then a lot of organisms use snails, and parasites use snails as part of the reproduction. So before it might come up and hurt humans, we might go and target the snails to kind of break the reproductive cycle of that pathogen. So it's really challenging to deal with these vector issues. Same with the zoonosis. Zoonotic diseases are usually, we're talking about transferred from other animals to humans, but there are cases where humans have given diseases to other animals. And this is in both terrestrial and aquatic settings. When I worked in aquariums particularly, when you have a tank system, it's an isolated system usually. It's that tank versus this tank. So we always had to be sure to wash our hands off in fresh water before we went from one tank to another, unless they were on the same system, because you don't want to introduce something. You don't want to transfer accidentally disease from one system to another. And yes, there were some diseases that can go from that tank to human. I had a friend working on coral tanks, and they picked up a disease on the skin working on it because they kept on nicking themselves on the corals, and there was something in the tank. So again, these things can go both ways, even though they're talking from other animals to humans. So do be careful with that. Like avian flu, working in close association with some organisms, obviously diseases can transfer. SARS might be a little bit of a complexing situation there. So there you go. There's your plus minus system in its wonderful grandeur. Now I wanted to show you something. One thing here at the end. These are complex systems. And so people forget that. And I have people say, well, wait a minute, haven't we been studying this for centuries? Don't we get it by now? Not necessarily. Here's a very famous event that I wanted to show you, the Battle of Kruger, where you get things sometimes that are unexpected. It's a little bit of a longer video, but I think it's worth your time. All right, so let me change over to my sound so that you can hear the video. On.
Really intently watching the movie, moving right over there. Be very interesting. That is a huge buffalo. A huge buffalo. Oh, they're too young. The one's gone already.
Don't you think I found that? Is it little?
I don't know. I think they're a bit young. I don't know. Maybe. They're crouching.
He's quite big.
Uh-oh. The ball gonna do. You got the baby. Get the baby what?
She got him. Oh, she did. She got him.
Baby, these babies just dropped that buffalo yet. Do you see that yet? Oh my God. Unbelievable. I'm shaking. Can you believe this? So the buffalo are coming to help this one now. Watch. They'll come and help this baby. Watch.
Can they help him out, son?
Yeah, they can.
He's still alive, you think?
Oh, it's still alive. Russell for fame.
You're trying to drag him out. You're dragging him out.
Hulle het nou net 'n kleintjie gevang. Hier's lekker action hier so jong. Hulle het 'n kleintjie hier so in die water en die krop is besig om nader te kom.
That's back.
Ja, positief. Hulle het 'n klein druppeltjie gevang hier so.
There's a crocodile there too.
Daar's 'n krokodil ook daar. 'n Krokodil op die kleintjie.
The
Ja.
crocodile. Yeah.
As you clear the bottom, the cock's trying to get the baby. Look at this. The crocodile's taking the baby away.
It's two crocodiles.
They're going to lose it.
Oh my God. Oh, they're going to fight over it. Oh my God. Oh, look at the
The lions of won.
lions are one.
Oh, the lions have won.
Yeah, but look at all those buffalo.
Oh, they're going to come and try and chase the lion, but I think they're too late.
I think you're right. No, we can remove. But then it takes it. Come on.
Now they're too late. Can you imagine?
For the people.com.
Oh, look at the teeth. We're gonna chase it.
They're too nervous.
You're too late.
Guys, you cannot believe what's going on here. There's a big area between lions, crocodiles, and buffalo.
Oh.
He swatted at him and kicked at him. He's kicking at him. Look. He's kicking at him.
Die buffels is bezig om die deels te omsingel. Die deels het een klein en daartoe gevangen. Daartoe sal die deels naar bykom. Hulle jaag die deels ons nou weg.
Oh, they got him surrounded.
Jy kan maar kom dan.
Not one.
Ooh.
Ooh.
Get the line on it, man.
The middle one is still alive.
Really? Look at the fish. But they're in. Yeah.
Oh, the leaf is still-
Never seen that.
I've never seen.
The calf's still alive.
Mhm.
Yeah, it's trying to get away. It's standing up.
Oh, hierdie buffels het die meeuws weggepak van haar kleintjie af. En
We're still chasing it.
And they keep.
I've never seen him shot.
Too much.
They chased him away.
But they hoek jou aan, en die still.
So there you go. Again, these are much more complex interactions that people often realize. And I wanted to note something back here, right about there. If you noted, there's a windmill right there. This is happening in some guy's backyard. Don't think that you have to be in South Africa or someplace like that for this to be taking place. You just pay attention to what happens in the world around you. And there's going to be amazing interactions out there. Okay, again, I hope you enjoyed this chapter. As always, if you have any questions, feel free to let me know.